You should all be familiar with Legionnaires' disease, atypical pneumonia, characterized by a fairly high mortality, 10 to 40%, 40% being if you should get it while you're a patient in hospital. The incubation period is usually considered to be between 2 and 10 days. We take a 14-day history when we were actually investigating outbreaks and cases, but there is some debate about this, and it isn't a nice U-shaped curve. It's got rather an extended end, and in fact 10 to 15% of cases will be found after 10 days. The symptoms, very vague. There are no specific symptoms you can say this person has Legionnaires' disease, although things like diarrhea, not so common with pneumonia, might be suggestive. And the other thing is really the severity of the systemic onset. That's just a picture of a typical lung that you would see with Legionnaires' disease. And I just want to mention, we often talk about the acute presentation, but in fact, it is not uncommon to get long-term problems, restrictive pulmonary disease and neurological problems being some of the biggest. And it's also a bit of a problem when we actually go to question people, because they do get this retrograde amnesia, and sometimes many of the key details are difficult to elucidate. This is just a very quick refresh for yourself. You should all be very familiar with this. There are over 50 Legionella species. Some of them are associated with human disease. Legionella serogroup 1, Legionella pneumophila, is the one that we're very interested in, and we believe is responsible for about 80 to 90% of all the infections. Of those, it's Legionella serogroup 1, which is one of 16 serogroups that we find to be the commonest cause of Legionnaires' disease. Now, the fact that the urinary antigen test that we use is actually specific for Legionella pneumophila serogroup 1 may also be a factor in why so many of the cases are Legionella serogroup 1. Case classification, this is important because we use a clinical diagnosis plus the presence of one of the three microbiological confirmatory tests, either isolation from a clinical specimen, the presence of urinary antigen, or less often now we look at seroconversion. And as you'll see later, serology really plays a very minor role now in Legionella investigations. So therefore, it's really very, very important that we get the microbiology right, because laboratory diagnosis is absolutely critical. Without this, we do not have a definition. Without this, we cannot then link individual cases to environmental isolates investigation. These are the four main methods. As I said, culture is considered the gold standard. Again, because not only do we identify Legionella pneumophila, but we also identify things like Legionella mcdadii, Long Beachii, etc. Serology plays very little part, perhaps in the investigation of outbreaks. There may be a small part, but by and large, it's very little used these days. Antigen detecting, urinary antigen I've talked about. You should all be familiar with that. And then finally, we've got nucleic acid, PCR, where increasingly this is being used. And in fact, I suspect in the very near future, we'll be including PCR as part of the confirmed Legionella case definition. Looking at the diagnosis and detection, in terms of both the clinical and the environmental aspects, culture, really important. Serology plays no part in environmental, and increasingly we're seeing nucleic acid both in terms of clinical and the environmental. One of the things that's made a very big difference in terms of the investigation of outbreaks and trying to identify the cause is the development of this sequence-based typing. And as many of you will be familiar, it's based on these 7 gene loci. I'm not going to go into them. You probably know more about it than I do. But all I need to know is that there is a very accurate way of subtyping Legionella. And in fact, I looked to my colleague Tim Harrison, who heads up the reference lab, for advice on this particular issue. I do know, however, that using a combination of these 7 genes, we can identify strings of these individual allele numbers, and we then have an SBT which seems to be fairly unique and which allows us to do accurate profiling and mapping mapping across human strains to environmental strains, etc. So this is all I think in the pack, and I don't intend to go into a lot of detail. I just want to try and raise the thing in your consciousness so that when we're talking about it later, hopefully it makes some sense. I think the important thing is, though, that culture, I think when we first looked at Legionella investigations back in the 90s and year 2000, very many of the cases, there was no sputum, there was no clinical specimen for culture. We've seen that increasing, in fact, in 2010 or 11, I can't remember which. About 26% of the cases, there was culture made. So that's quite an important step forward, because, as I say, that does allow us to link environmental specimens to clinical specimens and therefore identify potential sources. And this is just really giving you a feel for the way we would use it. In this context, I'm using the European travel scheme, where we presented with 2 patients, both in different countries, both developing Legionnaires' disease, and they've been to a place, let's say, in Paris or in Rome. We identify a number of hotels they stayed at, and in fact, we may even have a cooling tower. The first thing we'll do, we will identify its Legionella pneumophila, hopefully from culture, from clinical specimens, and then using some further MAB subgrouping, we can then try and further refine the examination so that by the time we get to the 4th layer, we can exclude things like Hotel C, we'd be able to exclude the cooling tower, whereas 10, 15 years ago, we'd have had a real problem. And then using the subtyping, we then are able to establish that, in fact, when you look at it, you've got an ST9 for Hotel A, and you're left with the ST2, which links the 2 clinical cases and the hotel. And that's really the basis of what we try and do when we're investigating potential outbreaks. We're trying to piece together the evidence, the information, so that we can link clinical and environmental cases. This is a picture of the surveillance form. It's actually about 6 pages long, fairly detailed. And in it, we try and collect useful information about what the patient has done, where they've been, etc., in the 14 days prior to the onset of their illness. We are looking to use this as a way of trying to see, based on severity, can we identify specific subtypes or ST subtypes, but we're not at that stage yet, and there's a bit of further work to be done. I think it's also important to say at this point that it's probably vastly underdiagnosed, and I think there's 2 reasons for that. One, it's often cheaper to treat than investigate, and I think you'll see from this, this is community-acquired pneumonia from some HES data, and you see that of 194,000, there were 194,000 unspecified community-acquired pneumonias. And these are instances where it's just been a treat and we won't investigate. So an enormous challenge there in trying to refine what actually the prevalence of Legionella is. However, there had been 2 studies done. One of them was done in Nottingham, which estimated that the prevalence was about 3%. Now, given that that would equate to 3,000 cases of Legionella, and we only see roughly 300, you can see there's a big disparity between what might be happening out there and what's actually being reported. These are the cases of Legionella. I've included confirmed and presumptive, and you'll see that up until about 2010, we were getting about 350 cases being reported each year. But for some reason, and I don't understand it, perhaps time will tell, we saw a sudden drop in the number of cases in 2011. These seem to be in the community acquired. In other words, the travel-associated cases remained the same, the nosocomial-related cases remained the same, but we did see quite a slump in the community-acquired cases. Moving on then, we talked about mortality, and this slide demonstrates 2 things. It shows the difference between the experience of men and women. The males have a 3 to 4 times are affected or diagnosed 3 or 4 times more frequently than women. Perhaps it's a behavioural thing. We know that smoking is a key factor, and that perhaps over time we will see women catch up as smoking works its way through the age cohort. And the other thing to note is the increase in the case fatality rate with age. Once you get into 70 and plus, there's quite a significant mortality, about 20%. Again, this is just really illustrating not just the difference in age and gender, but the difference in where you acquire your Legionella. And you'll see from this that acquiring it in hospital, has a much higher case fatality rate than, say, associated with travel abroad or even in the community. Over the last 10 years rather, we've seen at one point we hoped that we were seeing a downward trend in the case fatality ratio, then it went up. But over the last 10 years, we've seen it go from 9.1, and its most recent one is 8.1. You might, with the appropriate statistical test, be able to say that might be significant, but I'm not going to try and convince you of that. You just have to look at the graph, and hopefully what's happened in 2009, 10 and 11 will continue subsequently. These are the cases that, with Legionella, underlying medical conditions as well as age are an important factor. And really the two things to highlight: heart disease is a factor associated with number of cases, and smoking. Other factors variably associated, diabetes and immunosuppression being the other two factors. So people with heart disease and smokers, these are the group that are probably more likely to get Legionnaire's disease if Legionella is present. And I think the other important point to make at this point is that a lot of us, well, all of us could be exposed to the same level of Legionella, but only very few of us would actually get it. And there is some intrinsic factor within us that determines whether or not I get Legionnaire's disease and you don't. And things like heart disease, smoking are just some of the factors. And to be honest, we're not really clear about what the other factors might be. This is really just trying to show what I described a little bit earlier. In 2011, we saw this marked decrease. The cases that were travelled abroad really didn't change. We saw it go from just under 40% of all cases to about 53% of all cases were travel associated, and the biggest reduction was in community acquired cases in 2011. Legionnaire's disease, the diagnostic test, I put this up, it's really just to show that culture, which is a key element of Legionella, is improving. 26% of cases in 2011, and I hope that that continues. I think another important point to understand when we're looking at Legionella, we never find out the cases or the origin or the cause of it in over 70% of cases. So there is a real challenge when it comes to trying to identify potential outbreaks. Moving on then to look at things that are important in terms of the environment, and we see that these 5 elements are fairly key to the survival of Legionella in the environment. Stagnation, so anywhere where water can pool or lie is a potential source. They need nutrients. They act on a fairly wide range of pH, but tending toward the acidic. Temperature is really important, between 25 and 45 degrees. Another important thing is the association with other aquatic species. This is a slide, fairly old one, but nevertheless still relevant today, showing that really in order to get continued growth of Legionella, you really do need to have nutrients. The top line shows hot water in a tank. The other two is filtered water and pure water. And Legionella does not survive very long without the nutrients it would get from some of these sources within a normal hot water tank. These are just some of the organisms in which Legionella lives. An enormous number of amoebae can support Legionella, and living actually within a protozoal organizations is actually very protective. And this is quite a challenge when it actually comes to trying to treat systems that are already contaminated or colonized, because it can survive up to 50 parts per million of chlorine inside some of these organisms. So it's a real challenge when it comes to trying to eradicate, well, you can never eradicate, but to try and manage it. And it's also believed that because they will survive in these cysts, you can get Legionella carried up to 10, maybe even 12 kilometers from cooling towers as a way of distributing the infection. So a challenge when it comes to trying to manage and control this. And I think we're only fortunate that so few of the population are susceptible to it. Biofilms are a really key element when you look at Legionella in an environmental situation. And I'm not going to go into too much detail. Again, it's in the handout about what a biofilm is. But basically, you've got this initial conditioning layer, you then get a bacterial layer developing on top of it, and then eventually over a period of time, you get biofilm. And this is really just a schematic picture of some of the features of a biofilm and why it is such a problem in trying to manage. In terms of what encourages a biofilm, there's a variety of things. You've got organic carbon, you've got dirt, you've got debris, but most important is scale formation, and scale formation is a particular issue in the south of England and some parts of the country where the furring in the pipe provides an ideal opportunity for biofilm to develop. At this point, I'm going to ask, does anyone know what that is? Would anyone like to hazard a guess? Well, I don't think you'll guess, but does anyone know what it is? No? That's a filter from a TMV valve with a biofilm. That was taken from a hot water tap in a hospital where they were having recurrent problems with Legionella from that particular tap. So that was actually retrieved from a hospital filter in situ in a sink in one of the wards. And that was representing a build-up of biofilm. And that's the sort of thing that will present a real problem in trying to track down within a water system exactly what the problem is and the sort of remediation required. You'll see that not only does the biofilm actually protect it, but it also gives it some important benefits in terms of growth. We talked about temperature being an important feature, and this slide has really got 2 or 3 things on it. One, it's showing the optimum range within which Legionella will grow, 25 to 50 degrees on the right-hand side. And on the left-hand side, we've got the time it takes to kill 90% of Legionella population. And you'll see that very few Legionella survive beyond 2 minutes at 60 degrees, which is one of the temperatures that we set in terms of control of Legionella. 2 key temperatures, 20 and 60. Over in Europe, they actually talk about 25 and 55, but we've gone for 20 and 60 because of these 2 graphs. In order to actually disseminate the Legionella, we need to have a source of aerosol. And surprisingly, you get aerosols from just about anywhere where there's water. Water hitting a surface will create an aerosol. And all of these things have been associated at some point, probably, with the Legionella outbreak. In terms of infection via an aerosol, it's not the spray. If you can see it, it's not really an aerosol. Aerosols are virtually invisible. They're very small particles, and they have to be small because they go all the way down into the alveoli. And we talk about small particles of less than 5 micrometers, so they can be inhaled deep into the lungs. And the final point about aerosols is that they can travel long distances, which is an important element in terms of the investigation. This was a simple study just done looking at, how easy is it to generate an aerosol. And this was a study done some time ago with running a bath. You run the bath, you get a big upsurge in particles, you turn it off, and within about 10-15 minutes, they gradually start to go down so that about 20 minutes after turning it off, you're back to where you started. So something as simple as running a bath will create an aerosol and will be a means by which Legionella can be spread. In terms of survival, you'll see that, again, Legionella will survive for some time in certain conditions. Humidity is a clear clearly an important factor here, but given the propensity to actually survive within spores, it's not fundamental. Just before we go on to this, does anyone have a washing machine, a new washing machine? Do you notice anything about a new washing machine that you maybe didn't notice with your old one? Well, one of them is the new washing machines have only got one source of one pipe in, whereas old ones had a red one and a blue one, hot and cold. And usually what's happening now is that people are buying a new washing machine and they haven't bothered to cap off the existing piece of hot water pipe because that's too expensive, so they just fasten it onto the cold water. And in a sense, what they've then just created is a dead leg or a blind end, which Legionella will multiply, grow, and could over time invade your system and then cause potential problems. So it's very simple things like that when we're looking at how we investigate and manage Legionella, which can be highly important. The other things, again, which are important would be the choice of materials. And you'll see here, this was a study looking at Legionella growth using different materials. And something like latex, very good for growing Legionella. Something like copper will have a negative effect. So actually the material you use in your water system could actually be fundamental in trying to control Legionella within a hospital or within an environment. In thinking about Legionnaire's disease, this is the model I tend to use, the classic one of source, the vector, the host. And you need to have all three present, really, in order to get effective transmission of the Legionnaire's disease to occur. You need to have a source which is contaminated, you need to have a means of spreading it, the aerosol, and you need to have a susceptible host. And I think this little anagram, this little model, when you're actually looking at potential outbreak, is very important, especially when you're trying to carry out a potential risk assessment. If you've got contaminated water, but there's no way for an aerosol to be transmitted, in other words, a closed hot water system, then there's not a problem. So I think it's useful in terms of thinking about how you would approach a potential problem. This is some of the measures that we actually use in terms of trying to control Legionella. The formation of scale is a very, very important factor in some places, and therefore water softening is one way of trying to control the development of Legionella in the system. You reduce the scale, prevent corrosion, and hopefully reduce the habitat for the Legionella organism. In terms of design as well, I'm sorry this is getting slightly complicated, but when you've actually got a large hot water tank like this, there is a tendency for all the hot water to collect at the bottom. So some of the remediation measures we put in is what we call an anti-stratification pump. And basically that just tries to circulate the water from the bottom of the tank to the top. Now clearly, if you came across a tank like this on the left-hand side, there is a potential problem unless you've done this, because you will get an optimum temperature where Legionella would grow, and it's not uniformly hot throughout. So this is one of the ways in which we'd actually look to trying to minimize the risk of Legionella growing. In terms of looking at hot water systems, these are some of the issues that we try and address. We try and make sure that the quality of the water was good, that it was soft water. We try and clean and disinfect any tanks that we have. Any deposits that would appear, and it's actually quite quickly, you can get growth of deposits in any sort of storage tanks, and you would prevent any stratification occurring. One of the other important factors is actually water storage itself. If you have a storage capacity that will hold water for a month, you've got a real problem in terms of an emergency, because that is an ideal location for Legionella to grow. And increasingly we're seeing smaller tanks being produced, which is why some hospitals in the situation where they've maybe only got 1 or 2 days worth of water, because it's a measure to try and prevent another issue happening, such as Legionella. The key element in trying to maintain a conventional hot water system is trying to keep it as near 60 degrees as possible. And we do that with a variety of methods. However, one of the big issues and one of the problems is called thermostatic mixer valves. These are valves that were introduced to prevent scalding. They deliver water at about 40, 42 degrees at the point. However, they do produce their own problems. So while we may reduce the risk of scalding in some instances, we increase the likelihood of Legionella growing in another. So this is the classic, you're trading off one one risk against another. And then the final point in terms of conventional control is about eliminating stagnation. We've talked about blind ends and dead legs. A blind end is something where there is nothing beyond it. A dead leg is a redundant piece of piping, still connected, and in which you can get, if there's a drop in pressure, either material coming into it or out of it. And these are the real problem when it comes to looking at how we might address potential issues and problems in an institution. This illustrates really just some of the problems. We can get 55, 60 degrees leaving the hot water tank and 55 degrees returning it, which is some of the legislation. However, you can get dead legs. If I can work out how to do this, these are dead legs where there is no hot water circulating, and they can maintain temperatures of anywhere between 30 and 40 degrees. Ideal reservoirs for Legionella. And then finally, temperatures like this, ideal situation for Legionella to grow and intermittently work their way into the system. So really what I'm trying to do in describe some of these issues, sorry, I forgot this was done like that, is really just trying to understand the complexity. Identifying Legionella in the water system is really only the start. When we go on to look at specific issues, this was a hospital outbreak, and in fact, one of the components that have been used in the hospital system should actually have been used in our pipeline, not in a water system. And so you are dependent to a large degree on the contractors, the people putting it in, to know that they've done it properly and it's been done appropriately. And you'll see, just here, this scale resulted in almost an occlusion of the water, so that what you ended up with was stagnation and a potential source of Legionella. This is taken from a Yugoslavian outbreak in a hospital, and these were pipes that were actually buried in the wall. And despite all the efforts originally of the hospital to try and find out the cause, they could not find it. But by progressive sampling, were able to narrow it down to one section, at which point they decided to go into the wall. And when they got into the wall, they found that there were some blind ends. In other words, someone had at some point decided to revise the plumbing. Instead of taking it off and doing it properly, they just capped the end, and therefore this was a source of Legionella in that particular institute. And until that was remedied and rectified, they had problems. This is the length of the piping, 110 centimeters long. That was the problem they had for a number of years, just this small 10 centimeter length of piping buried in the wall. It says 15 millimeters, that's a mistake, it should be 150 millimeters. Sorry about that. But until that was removed, they had Legionella problems, and once it was removed, it went away. This is another example of what we can run into. The bit on the left is a TMV valve, all nicely insulated, but nothing else has been insulated. You've got cold water, hot water pipes, all mixing in the same area. The ambient temperature in that place was 35 degrees, no insulation, and so the cold water was being heated up to what was an ideal temperature for Legionella to grow. And although the TMV was working properly, actually the water going into it was already 35 degrees, and the amount of mixing was minimal. Another example of domestic situation you might see at home, a sort of boiler which is turned into a heating cabinet. Again, you can keep the temperatures effectively fairly high. Moving on then to spa pools, and this is one of the issues that we've seen recently. Spa pools are a fairly new thing in the UK. But actually, these are incredible sources of Legionella and other organisms, Pseudomonas being one of the other one that comes to mind. You can get them in a variety of places, and each one of these, these locations has been associated with outbreaks or individual cases. So they have enormous potential to cause infection. And that's because you've got a number of factors working here. Warm water, it's usually aerated, although it's often treated and not emptied between each use, and you get lots of people using it, so there's lots of carbon and tissue generated by the continued usage. They're also very difficult to keep clean. This is a large one, and one of the favourite places when we go out sampling is actually to look in these vents, because they're very incredibly difficult to clean. And when you take swabs, invariably you tend to find some level of colonisation with Legionella. So again, the problems with the spa pools: large surface areas, the quality of water, lots of carbon in there, tend to get poor management. Everyone hates looking after the spa pool. You know, you've got to do all sorts of things. It's fiddly, no one likes it. But actually it's one of the most important things to do in terms of monitoring, as we've seen recently. I put in this was a spa pool associated with somewhere not far from here actually, where people would go to meet other people and you would indulge in various things. And you can imagine there was quite a lot of carbon in organic material in these spa pools. But the point I really want to make is that you have these seating areas, very, very difficult to clean. You have the water level actually above and slopping into the floor. Whoops, to the floor there, and there are real challenges when it comes to trying to treat that. I just want therefore to acknowledge all the people that have helped put these together, because as I say, the one thing you do realise is managing Legionella is a team effort. No one person can do it on their own. And I hope stimulated interest and maybe hear from you in the future. Thank you.